Germany, 1911. A meteorologist named Alfred Vegner was browsing through some books when something caught his eye. A list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Vegner was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar. How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Vegner saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaea, meaning all earth. It was in Pangaea that the plants and animals found on opposite sides of the world had once shared the same home. Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Vegner called his theory continental drift. Vegner wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive. There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe. As a result, his discovery was largely ignored. World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this: flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains, like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific mountain range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was: a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge. To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the mid-Atlantic ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
That the earthquakes...
Hess's discovery that the seafloor was spreading rescued Alfred Wegener's idea of Pangea from obscurity. Now there was a geological mechanism to explain continental drift.
That's simple.
Once you hear it, it sounds great.
It does sound great.
By the 1960s, both ideas were synthesized into a single theory, the science of plate tectonics. A great discovery that revealed just how complex and dynamic our planet is. Several groups of scientists had concluded that not only is the Earth's crust moving, but the surface of the planet is broken into large, interconnected plates. These plates are constantly in motion, floating on a layer of molten rock in the Earth's mantle.
It seems fantastic. I mean, it seems just too crazy. How could the whole world be sliding around? I can see where people were skeptical.
That's right, that's right. But it's the rates that your fingernails grow.
It's not very fast. I don't feel a thing.
That's right.
Yeah.
But cumulatively, it's huge. So here's the thing is geologic timescales is what makes this so important, because if you think of it over a year, you move a few centimeters. If you think over millions of years, you're moving kilometers. About 250 million years ago, all the plates were together in Pangea, and they're moving apart, and they will come back together again.
Why do they move back together?
Because the Pacific Ocean right now has subduction all around it, and the plate is actually being consumed and recycled, where the Atlantic Ocean is spreading without much subduction. So the Atlantic Ocean is going to grow, the Pacific Ocean is going to close, and then we'll start getting closer to Asia and closing up the Pacific Ocean.
It's crazy.
It's pretty great.
Crazy.
And once you hear it, it's hard to imagine geologists not believing in it. So once the theory and the mechanism, that was the important contribution.
Because no one would believe it till they had it.
That's right. So the plates are spreading, they're not plowing.
The understanding of plate tectonics has given scientists new insights into the changing face of our planet. A dynamic example of some of those changes can be seen here on the California coastline, where two of the Earth's largest plates, the Pacific and the North American, collide.
There's a number of results, but one, we get volcanoes where the plates are subducted back into the Earth. These volcanoes happen because the plate that gets subducted releases water, and this water lowers the melting temperature of the overriding plate and makes it easier, and we get volcanism.
So that's where you get Mount Whitney, Mount Shasta.
Things like this, absolutely. The Andes are a perfect example of these type of volcanoes. Other places you get the mid-ocean ridges. You get pieces of the seafloor that are 1 to 2 kilometers higher than the surrounding seafloor. These are underwater volcanic chains that stretch the length of these ocean basins. Other places you get large strike-slip faults.
So what's a strike-slip fault?
A strike-slip is when the plates move by one another, okay? And they don't do it without kinks and twists. And so where the kinks and twists are, there can be places that lock.
Yeah.
and then they release, and they release quickly with a lot of energy or momentum,
Tipping over buildings and so on.
causing a lot of shaking, yes.
But without earthquakes, you never would have found all this stuff, right?
Earthquakes are really important because they've allowed us to define the plate geometries. They've allowed us to define the boundaries.
So what about volcanoes?
Before volcanoes light off, a lot of times there's pre-eruption seismic activity.
Shaking.
Yes, yes. As the magma ascends to the surface, it causes stress, and the stress is released.
Do you see evidence of plate tectonics right here?
Yes. What we're looking at in the sea cliffs, these sediments were deposited about 500 meters below the sea level, and they've been uplifted. So here, we're looking at plate tectonics in our own backyard.
So far, we've explored what several great discoveries have revealed about what's happening inside the Earth. The next discoveries opened our eyes to what's happening above.